Somewhere in a lab, a machine just did in 5 minutes what would take the fastest supercomputer on Earth 10 septillion years to finish. Not 10 years, not 10,000, 10 septillion. A number so large that if you tried to write it out in seconds, you'd run out of universe before you ran out of zeros. Say that number slowly, 10 septillion. That's a 1 followed by 25 zeros. The universe itself is only about 14 billion years old. So the machine we're talking about didn't just beat a supercomputer. It beat the entire lifespan of the cosmos over and over again, 1 trillion times over, and it did it while you were still deciding what to have for lunch. This isn't science fiction. This isn't a thought experiment cooked up by a physicist with too much chalk and not enough sleep. This actually happened, it was published, it was peer-reviewed, and it is quietly rewriting what we thought was possible with computation. And the strange part is, most people have no idea it happened at all. While the world was distracted by the next viral video or the next election headline, a handful of researchers and a handful of labs were quietly proving that the fastest machines humans have ever built, the room-sized, electricity-hungry, multi-billion-dollar supercomputers that model hurricanes and simulate nuclear stockpiles, have a rival. And that rival doesn't play by the same rules. Let's start with what actually happened, because the details matter more than the hype. The machine in question is a quantum processor. Not a bigger, faster version of your laptop. A fundamentally different kind of computer. One that doesn't store information as ones and zeros, but as something called qubits, which can exist as 0, 1, or a strange blend of both at the same time. If that sounds impossible, that's because it defies everything your intuition has learned from a lifetime of using regular computers. But it's real, and it's the reason this new generation of machines can explore an almost incomprehensible number of possibilities simultaneously, instead of checking them one after another the way every computer you've ever owned has to. Think about a maze. A classical computer, no matter how powerful, has to try one path, hit a dead end, back up, try another path, and repeat that process until it finds the exit. It might do this billions of times a second, but it is still doing it one path at a time. A quantum computer, in a very real sense, can wander down many paths of that maze simultaneously, using the strange physics of superposition to explore possibilities in parallel rather than in sequence. When the maze is simple, this advantage doesn't matter much. But when the maze becomes staggeringly complex, the kind of complexity you find in molecular structures and cryptographic codes in the physics of subatomic particles, that advantage stops being a curiosity and starts becoming a chasm. The team behind this particular breakthrough used a benchmark called random circuit sampling. Think of it as the toughest workout routine you can give a computer. Not because it's useful in itself, but because it is brutally, mathematically difficult for any classical machine to fake or shortcut. It has become the standard test in this field precisely because it's unforgiving. If a quantum chip can't beat classical computers at this benchmark, there's little reason to believe it can do anything more sophisticated. It's the entry exam before the real coursework begins. And this particular chip didn't just pass the exam, it obliterated it, running a calculation in under 5 minutes that would leave the world's most powerful classical supercomputer chugging away for that almost unthinkable stretch of 10 septillion years. But here's where the story gets more interesting and more important than just a big, scary number. Big benchmark numbers have shown up before in this field, and they've been met with skepticism, and sometimes rightly so. Back in 2019, an earlier generation quantum chip made headlines with a similar claim. A calculation completed in 200 seconds that researchers estimated would take a top supercomputer 10,000 years. That claim triggered a wave of counterattacks from classical computing researchers, who spent months developing smarter classical algorithms that closed much of the gap. It turned out that 10,000 years was a moving target, not a law of physics. Engineers found clever tricks. Supercomputers got faster. The gap shrank. So when a new claim shows up promising an even bigger gap, the reasonable question isn't, wow, 10 septillion years, that's incredible. The reasonable question is, will this gap shrink too? And that is exactly the question this newest generation of research was built to answer, because this time the team didn't just run an abstract synthetic benchmark. They ran a verifiable algorithm on real hardware, doing something with actual scientific value. Researchers described it as the first time in history that a quantum computer successfully ran a verifiable algorithm on hardware that surpasses the ability of supercomputers. That word, verifiable, is doing a lot of quiet, careful work in that sentence. It means the results can be checked, confirmed, and trusted, rather than simply asserted. In that particular test, a quantum computation running on 65 qubits was estimated to take a top supercomputer 3.2 years to complete. The quantum processor did it in 2.1 hours. Read that again slowly. 3.2 years of continuous supercomputer time, compressed into a single afternoon. And unlike the earlier random circuit sampling benchmark, this wasn't an artificial stress test designed purely to be hard. This was closer to the kind of calculation that actually matters for real science, the kind used to understand molecular behavior, chemical interactions, and the underlying structure of matter itself. That distinction between a synthetic benchmark and a genuinely useful calculation is the heart of why researchers are using the word permanent, and why this moment feels different from the false starts of years past. A synthetic benchmark can be gamed. Someone can write a smarter algorithm, throw more processing power at the problem, and slowly claw back the gap, the way classical researchers did after that first 2019 claim. But when a quantum machine solves an actual scientific problem faster than any classical alternative, and does it in a way that can be independently verified, the game changes. You're no longer arguing about whether a magic trick has a hidden classical explanation. You're looking at a working tool that does real work faster than anything else humanity has ever built. And this wasn't a one-off party trick either. The same research team went further, applying similar quantum hardware to a molecular structure calculation, the kind of problem that matters enormously for drug discovery and materials science. In that experiment, the quantum system completed the simulation in about 5 minutes. The best classical supercomputer, researchers estimated, would need roughly 10 septillion years for the same task. That's the number we opened with, and it wasn't chosen for shock value. It was chosen because it's the actual estimate, calculated by scientists who have every professional incentive to be conservative rather than sensational, because their careers live and die by peer review, not by clicks. Now, you might be wondering, if this is such a slam dunk, why hasn't quantum computing already replaced every supercomputer on the planet? Why are we not already living in some quantum-powered utopia where every disease has been cured and every code has been cracked? The honest answer, and the one serious researchers in this field will actually give you if you ask them directly, is that quantum computing is still nowhere near a general replacement for classical computing. It is not commercially useful at scale yet. Most of these breakthroughs remain confined to research environments, specialized simulations, and carefully controlled pilot programs, not everyday business operations or your personal laptop. The reason for that caution comes down to one brutally difficult engineering problem. Qubits are fragile. Extraordinarily, maddeningly fragile. Unlike the bits in your phone, which sit there stubbornly as ones and zeros no matter what you throw at them, qubits interact with their environment in ways that corrupt their information almost instantly. A stray vibration, a tiny fluctuation in temperature, even a whisper of electromagnetic interference can cause a qubit to lose its delicate quantum state, a process physicists call decoherence. For years, this was quantum computing's central curse. The more qubits you added to try to solve bigger problems, the more errors accumulated, and the errors piled up faster than anyone could correct them. It was like building a skyscraper out of sand. Every additional floor made the whole structure more likely to collapse before you finished it. The theoretical fix for this problem, known as quantum error correction, has actually been understood since the mid-1990s, when the foundational framework was first described. But understanding a solution on paper and actually building it into working hardware are two very different challenges. And for 3 decades, engineers struggled to close that gap. What makes this most recent wave of breakthroughs so significant isn't just the eye-popping speed comparisons. It's that researchers finally demonstrated something called exponential error suppression. In plain language, that means that as they added more qubits to the system, arranging them in larger and larger grids, the error rate didn't spiral out of control the way it always had before. Instead, performance actually improved. The skyscraper, for the first time, got sturdier as it got taller instead of shakier. This is the detail that most casual coverage of quantum computing completely glosses over, because a giant number like 10 septillion years is a much easier headline than the phrase exponential error suppression. But error correction is the actual story. It's the difference between a fun magic trick that only works once under perfect laboratory conditions and the beginning of a technology that can scale, generation after generation, towards something genuinely useful. Every field of engineering has a moment where a wild theoretical possibility turns into a stable, repeatable process. For quantum computing, this may be that moment. It also helps to understand just how competitive this race has become, because breakthroughs like this one rarely happen in isolation. Major technology companies are pouring staggering sums into quantum research, racing not just to build more qubits, but to build qubits that behave better, that hold their fragile quantum states longer, and that connect to each other with fewer errors. One company has bet on superconducting circuits cooled to near absolute zero. Another has bet on trapped ions, individual atoms suspended and controlled with lasers. Yet another is chasing an entirely new class of particle altogether, hoping it will prove inherently more stable than anything built before. National governments have joined in too, treating quantum computing the way earlier generations treated the race to split the atom or the race to the moon, as a strategic technology too important to leave entirely to private industry. Multiple countries have launched dedicated national quantum strategies, funding research centers, subsidizing chip fabrication, and quietly competing to be the first to demonstrate a truly fault-tolerant machine at meaningful scale. That level of investment from governments and corporations alike is itself a signal. Nobody spends billions of dollars chasing a technology they believe is a dead end. And it's worth noting that progress in error correction research alone has more than tripled in published output within roughly the span of a single year, a pace of acceleration you typically only see once a field has crossed from theoretical curiosity into genuine engineering momentum. Naturally, this isn't the only lab making bold claims, and it's worth being honest about that too, because a healthy dose of skepticism is exactly what separates real science from marketing. Around the same period this research was published, a competing quantum computing company put out its own claim of quantum advantage, solving a different kind of problem on its own quantum processor faster than any classical computer could manage, and publishing those results in a separate, equally rigorous scientific journal. Two competing labs, using different hardware architectures, both independently claiming to have crossed this threshold within months of each other. That's not a coincidence, and it's not marketing hype feeding off itself. It's a sign that multiple independent teams, using fundamentally different approaches to building a quantum computer, are converging on the same conclusion at roughly the same time. In science, when independent groups using different methods arrive at the same result, that's usually the strongest kind of evidence you can get. But let's steelman the skeptics for a moment, because they deserve a fair hearing, and honestly, a smart viewer should demand one. Classical computing has surprised everyone before. Just months after some of these quantum claims made headlines, a separate team of researchers used one of Europe's newest and most powerful supercomputers to fully simulate a 50-qubit quantum computer for the first time ever, shattering the previous 48-qubit simulation record. That's an enormous classical computing achievement in its own right, and it's a reminder that classical machines are not standing still while quantum computers grab headlines. Every time quantum researchers push the frontier forward, classical researchers push back, finding cleverer algorithms, cleverer shortcuts, cleverer hardware architectures of their own. There's even more evidence of that classical pushback. Separately, a team of physicists developed an entirely new mathematical method that allows certain complex quantum systems to be simulated not on a room-sized supercomputer, but on an ordinary laptop. Their approach expanded on a decades-old technique from the 1970s, translating dense, nearly impenetrable equations into something researchers say can be learned by a physicist in about a day and used to tackle serious problems within a week. That's the kind of quiet, unglamorous progress that never makes it into a viral headline, but which genuinely matters, because it means some of the tasks that once seemed to require exotic quantum hardware might, with the right mathematical trick, be solvable on the machine sitting on your desk right now. So which is it? Is quantum computing permanently ahead, or is classical computing still capable of catching up? The honest answer, the one that respects both the evidence and your intelligence as a viewer, is that it depends entirely on which specific problem you're talking about. Quantum advantage was never meant to be a single light switch that flips from off to on for all of computing everywhere, all at once. It's task-specific. For certain narrow but genuinely important problems, particularly ones involving simulating quantum systems themselves, like molecules, materials, and particle interactions, quantum computers appear to have opened a lead that classical machines may never close because the underlying physics of the problem is quantum in nature to begin with. For other tasks, especially the kind of raw brute force calculations that classical supercomputers have been optimized to handle for 70 years, classical machines continue to hold their own and sometimes even extend their lead through clever new algorithms. This is precisely why the framing matters so much. When a headline says a lab has proven that quantum permanently beats supercomputers, it's tempting to hear that as a total, sweeping victory across all of computing, the way a boxing match ends with one fighter's hand raised and the other one on the canvas. That is not what happened, and any honest account of this research has to say so clearly. What actually happened is narrower, and in some ways more interesting. For a specific, scientifically meaningful class of problems, ones with real value to chemistry, physics, and material science, a quantum machine solved something faster than any classical alternative, using results that other scientists can check and confirm. That gap, for that specific category of problem, does not appear to be closing the way earlier. More synthetic benchmark gaps did. And that distinction, task-specific but durable, is what real experts mean when they talk about a permanent shift, rather than sloppy journalists looking for a bigger headline. Why should any of this matter to you? If you're not a physicist, not an engineer, and not personally invested in who wins the race between quantum bits and classical bits, because the applications sitting downstream of this breakthrough touch almost every part of modern life. Consider drug discovery. Right now, designing a new medication involves an enormous amount of trial and error, testing how different molecular structures interact with the human body. a process that can take a decade and cost billions of dollars per approved drug. Quantum computers, because they are fundamentally built on the same strange physics that governs molecules in the first place, are uniquely suited to simulating those molecular interactions directly, rather than approximating them the way classical computers are forced to. Early experiments using quantum hardware to simulate medical device interactions and molecular behavior have already begun, hosted by research teams working directly with quantum computing companies. Consider materials science next. Somewhere out there is material that could make batteries last 10 times longer, or a superconductor that works at room temperature instead of requiring impossibly cold refrigeration. Both of those breakthroughs, if they exist, are buried inside molecular configurations so complex that classical computers simply cannot model them with enough precision to find the answer. Quantum computers, built from the same quantum rules that govern those materials, may be the only practical way humanity ever discovers them. Several major technology companies have already partnered with aerospace firms, medical research centers, and national laboratories specifically to explore these applications because they believe the timeline for genuinely useful, real-world quantum advantage is now measured in months, not decades. And then there's the part of this story that makes people nervous, the part involving cryptography. Most of the digital security protecting your bank account, your medical records, your private messages, and honestly, your entire online life, rests on a mathematical assumption that certain problems, like factoring extremely large numbers, are practically impossible for any classical computer to solve in a reasonable amount of time. That assumption has held for decades. It's the quiet foundation underneath almost the entire internet. Quantum computers, in theory, are uniquely suited to attacking exactly that kind of problem, using an algorithm that has been understood mathematically since the mid-1990s, long before anyone had a machine capable of actually running it. For years, this threat felt purely theoretical, safely tucked away in some distant future, because building a quantum computer with enough stable qubits to actually run that algorithm against real encryption seemed impossibly far off. That distant future is getting closer, faster than most people realize. Researchers now estimate that breaking widely used encryption schemes may require roughly 10,000 stable qubits, a dramatic drop from earlier estimates that put the number in the millions. That's still beyond what any lab has built today, but the gap is shrinking in a way that has governments and security agencies paying very close attention. This is exactly why so much current research into what's called post-quantum cryptography, encryption designed specifically to resist an attack from a future quantum computer, has accelerated dramatically over just the past 2 years. It's not paranoia, it's preparation, driven directly by results like the ones we've been describing. It's worth pausing here to appreciate just how strange this whole field really is, because it's easy to get lost in numbers like 10 septillion and forget how genuinely bizarre the underlying physics remains, even to the people building these machines. A qubit isn't simply a faster bit. It exists, in a very real physical sense, in multiple states simultaneously until the moment it's measured, at which point it collapses into a single definite outcome. Entangle two qubits together, and measuring one instantly tells you something about the other, no matter how far apart they are. A phenomenon so strange that Einstein himself famously distrusted it, calling it spooky action at a distance. These aren't metaphors researchers use to make the science sound cooler for television. This is the literal, measured, repeatedly verified behavior of the universe at its smallest scales, and we are only now building machines precise enough to actually harness it for computation, rather than just observing it in a physics experiment. That's part of why this story deserves more attention than it's getting. We are living through the opening chapter of a technology that could reshape medicine, materials, energy, and security within the working lifetime of people watching this right now. And unlike some technological revolutions that crept up slowly, with early clunky versions circulating for decades before anyone noticed, this one has a very specific, datable inflection point. Researchers can point to the exact benchmark, the exact hardware generation, the exact published paper where the error correction curve finally bent the right direction, where adding more qubits made the system more reliable instead of less. That is a genuinely rare moment in the history of any technology, the kind of turning point that textbooks decades from now will circle back to and say, this is where it actually started working. None of this means the skeptics should be dismissed, and a good storyteller or a good scientist never pretends complexity away just to build a cleaner narrative. Quantum computers today remain extraordinarily expensive, require extreme cooling, sometimes to temperatures colder than deep space, and are nowhere near ready to sit on a desk or in a data center the way classical machines do. The specific advantages demonstrated so far apply to a narrow, if expanding set of problems, not to every kind of computation humans care about. Major companies working in this space themselves acknowledge that the phrase quantum advantage gets thrown around too casually in media coverage, treated as a binary switch rather than the nuanced, task-specific milestone it actually represents. Being honest about those limits doesn't diminish the achievement. It makes the achievement more credible because science that admits its own boundaries is science you can actually trust. So where does that leave us, standing at this strange crossroads between skepticism and genuine astonishment? The evidence, published, peer-reviewed, and independently replicated by more than one research group using different hardware, points toward something real. Not a total, sweeping victory of quantum over classical computing across every possible task, but something arguably more interesting. A durable, verifiable advantage in a specific, scientifically crucial category of problems, the kind involving molecules, materials, and the deep physics of matter itself. That advantage doesn't appear to be the kind of illusion that evaporates the moment classical researchers write a cleverer algorithm, the way it did back in 2019. It appears to be structural, built into the very physics of the problem, which is exactly why researchers are using words like permanent, carefully and deliberately, rather than recklessly. The machines behind these numbers are still young, still fragile, still confined mostly to research labs and specialized partnerships rather than everyday life. But so was every transformative technology once. The first computers filled entire rooms and could barely outperform a skilled human with an abacus for certain tasks, and yet within a few decades they reshaped the entire planet. The first airplanes flew a few hundred feet before crashing into sand dunes, and within 70 years humanity was walking on the moon. Revolutionary technologies rarely announce themselves with a single, unmistakable moment that everyone immediately recognizes. Usually, they show up quietly, buried in a peer-reviewed paper, verified by careful scientists who choose their words far more cautiously than any headline ever will. And it's only years later that the rest of us look back and realize exactly when everything changed. If this research holds up, and every early sign suggests that it will, then the moment we've just described, a machine completing in minutes what would take a classical supercomputer longer than the age of the universe to finish, may end up being one of those quiet turning points. Not the kind that trends for a single news cycle and then disappears, but the kind that shows up decades from now in a textbook, in a single carefully worded paragraph, marking the exact place where computation, medicine, materials science, and cybersecurity all began following a different curve than the one we expected. We may be watching the opening minutes of that story unfold right now, largely unnoticed, in a handful of labs, on a handful of chips, running calculations that no classical machine on Earth, no matter how large, how fast, or how many rooms it fills, will ever be able to catch. And if that's true, then the real story here isn't just a number, a benchmark, or a headline. It's the quiet sound of a new era of computation switching on.